Hello, let's continue with Chapter 5. First thing I want to talk about is unusual probabilities. Now we say a probability is unusual if it is less than or equal to 5%, 0.05. Okay? Or if you compute the z-score, or if the z-score is less than -2 or greater than 2, then we say it is unusual. Okay? Now when we say unusual, we mean statistically unusual, not unusual in the English sense. So for example, if we're looking at height and somebody has a z-score that is equal to 2.64, this means that they are 2.64 standard deviations above the mean, and that means that that person is unusually tall. Okay? If you calculate the probability that somebody will be 70 inches tall and you get 3%, then that's an unusual probability, okay, of them being that tall. Let me show you where this comes from. If you remember the 68, 95, 99.7 rule, remember 68% of our data is within 1 standard deviation of the mean, 95% of the data is within 2 standard deviations of the mean. Okay, 95% of the data is within 2 standard deviations of the mean. So if I'm looking at the normal distribution, remember the standard normal distribution. The standard normal distribution, I'll just abbreviate, standard normal distribution is normal with a mean of 0 and a standard deviation of 1. Then this would be 2 standard deviations, this would be -2, but this is considered a z of 2 and -2. 95% is between that, and then 5% is outside. So let me write that here. 5% of the data is on the outside, here and here. So if somebody is more than 2 standard deviations of the outside of the mean, that means that they are they have a probability within that 5%. Okay? So that's the linkage between z-scores. So that's the link between z-scores and probabilities and the empirical rule. Okay. Let's do an example using probability distributions. Let's look at this example right here. So if you go to your book and look on page 209, this is number 10. So groups of 5 babies are randomly selected, and each group, the random variable x, is the number of babies with green eyes. Okay, so x is the number of babies with green eyes. And I want to know what is the probability, and so here is the probability distribution table you can see right here. And I want to know what's the probability that 3 or more babies have green eyes. 3 or more babies have green eyes. So this was on page 209. What's the probability? And x represents the number of babies with green eyes. Now I want to know what's the chance that x is greater than or equal to 3. So if you look at this example, the probability distribution, we want to add up these 3 probabilities. The chance of 3 babies having green eyes, 4 babies having green eyes, and 5 babies having green eyes. And this 0 plus means that the probability is so small it's essentially 0. So that's 0.013 and 0.001. So if you add that up, you get 0.014. so which is 1.4%. Now, is it unusual to find, in a group of 5 babies, to find 3 or more babies that have green eyes? Yes, it is unusual because this is less than 5%. Remember our unusual probabilities rule right here? This is less than 5%. So, among 5 babies, it is unusual to find 3 or more that have green eyes. Okay? Let us look at something called the binomial probability distribution. Okay? The binomial probability distribution, or the binomial distribution, results from a procedure of a fixed number of independent trials where there are 2 outcomes in each trial, and the 2 outcomes we say are success and failure. It doesn't mean, success and failure that we think of it, but 2 outcomes. One of the outcomes is what we want to happen, and one of the outcomes is what we're not interested or what we don't want to happen. So that's why we call it success and failure. Okay? 2 outcomes in each trial, and the probability, and I'll just abbreviate probability as PROB, the probability of success is the same in each trial. I know that's a long definition, but that is what a binomial distribution is. There are 4 properties in this definition that I want you to pay attention to. Okay. The first is that we have a fixed number of independent trials. A fixed number of trials. The second one is that the trials are independent. The third is that there are only 2 outcomes in each trial. And the fourth is that the probability of success is the same for each trial. So these are the 4 properties that must be satisfied in order for us to have a binomial distribution. And if these 4 properties are satisfied, then we can use the formulas that I will show you now from the binomial distribution. Okay? There is some notation on page 213 in your book that I want to review. Okay? So let's take a look at that. Okay, so on page 213 in your book, you see this notation. Okay? So the probability of success, or the probability that we want to measure, is P, and the probability of failure is Q. Now P and Q are complements. If one happened, the other does not happen. So that's why Q is written as 1 minus P. Lowercase n, usually we are used to seeing lowercase n denote the sample size, but here for binomial distribution, n denotes the fixed number of trials. Okay? X is the number of successes. Again, P is the probability of success, Q is the probability of failure, and P of X is the probability of getting exactly X successes among the n trials. Okay? Let's do an example, okay, and identify whether a situation is binomial or not. So let me go back to my blue ink here. So first thing I want to look at is having a girl among 4 children. is that, ooh, something happened to my pen and now it's not working properly. Having a girl among 4 children. Do we have fixed trials? A fixed number of trials, yes. We do have a fixed number of trials. How many trials are we going to look at? We're going to look at 4. That's what the 4 children represents, the 4 trials. Are there only 2 outcomes in each trial? Yes. What are the 2 outcomes? Either you can have a boy or a girl. Okay. Are each of the trials independent? Yes, they are. Having a girl the first time does not affect whether you're going to have a boy or girl the second time, which does not affect the outcome of the 3rd child, and so on. Okay? So each trial is independent. And the 4th, is the probability of success the same on each trial? That's also true. You might have heard that there's a 50-50% chance of having a boy and girl, but I read somewhere that the chance of having a boy is 51% and the chance of having a girl is 49%. I don't know if that's true or not, but it doesn't make a difference because the chance of having a girl the first time is the same as having chance of having a girl the second time. So the probability of having a girl is the same every time. Okay, and here we're calling having a girl success because that's the outcome that we are interested in. So yes, all 4 properties are satisfied, so this is a binomial distribution. Okay. What's n here? N is the number of trials, that's 4. What's the probability of having a girl? Let's suppose I believe that article that I read and where there's a 49% chance of having a girl. That's P. Q is 1 minus P. This is the chance of having a boy, right? This is the chance of failure in this case. And 1 minus P is 1 minus 0.49, which is 0.51. Okay? And then X would be the number of girls. So for a binomial distribution, you always first thing you want to do is identify N, P, Q, and X. Okay, and that makes the problems that we're going to work on a lot easier. Let's look at another example. Among a group of 5, okay, so among a group of 5 peas, I want 3 green peas. Okay, and this is actually an example in your book on page 214. So let's go down and look at this example. Okay, so this is 5 offspring peas are generated from 2 parents, each having the yellow-green combination, and the chance of having a green pea is 75%. Okay, does this procedure result in a binomial distribution? And if it does, then identify N, P, Q, and X. Okay, and we want to find the probability that exactly 3 of the 5 are gonna have a green. 3 of the 5 will be green. Okay, so do we have a fixed number of trials here? Yes, 5. Is each trial independent? Yes. The probability of the first does not affect the probability of the second, and so on. Okay. 2 outcomes, and we're looking at either green or not green, right? So that's 2 outcomes, and the 4th one is a probability of success the same in each trial. Well, we know there's a 75% chance, so the chance of having a green pea 75%, that's going to be the same for each trial. So this is a binomial distribution. What's N here? N is 5. X is 3 because we want exactly 3 green peas. P is 0.75 and Q is 0.25. Again, Q is 1 minus P. Okay? Now, how do we find the probability of exactly, what's the chance of getting exactly 3 green peas among 5? Okay. There's 2 ways to do this. You can use the formula, which is here, or you can use the calculator method. Let me show you the formula first, then I'll show you the calculator. Okay. So if you look at this formula, the probability of x is n factorial, and this exclamation point is factorial, and I'll tell you in a minute what that means, divided by n minus x factorial times p to the x times q to the n minus x. Okay? So, n factorial over x factorial times n minus x factorial, p to the x, q to the n minus x. Factorial, this is the probability of x. Okay? Factorial means, like, if I have 3 factorial, that's the exclamation part, 3 factorial, that means 3 times 2 times 1. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So you just take that number and multiply until you get all the way down to 1. Okay? So let's look at this green pea example. Okay? And remember, n was 5, p is 0.75, q is 0.25, and x is 3. So plug that into the formula. 5 factorial divided by 3 factorial. 5 minus 3 factorial. P is 0.75 to the x. Q is 0.25 to the n minus x. N minus x. What's 5 minus 3? 2. So let's just write this as 2 factorial. Okay. Now 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. I really don't need to write the times 1 because anything times 1 is itself. Okay. That's 3 factorial, and then 2 factorial is 2. 0.75 to the 3. 0.25 to the 2. The 3 and the 2 here. The 3 and the 2 here cancel out with the 3 and the 2 here. At the top I'm left with 5 times 4. 5 times 4 is 20, divided by 2 is 10. That's 10 times 0.75 to the 3 times 0.25 to the 2. Okay. This you can plug into our calculator. Just plug it in just like that. 10 times 0.75. If you go to math, whoops, I didn't type in the 75. Oh, let's start again. This is not going. 10 times 0.75 to the 3rd power, and you can do math and press number 3 and you get 3rd, times 0.25 squared, and we get 0.264. Okay. If you want to do factorials on the calculator, you can go to math and then go over to PRB, probability, and number 4 it gives you the calculator sign. I mean the factorial sign. So you can put a number. Whoops, I think I hit the wrong thing. So if I wanted to calculate like 7 factorial, I could go to 7, hit math, go over, and then hit number 4. And then that would tell me what 7 factorial is. And that's 5,000. That 5,040. That's 7 times 6 times 5 all the way down to 1. Okay? So that's using the formula. Luckily, you don't have to use the formula because there's a neat shortcut that we can do on the calculator. And that function is called the Binomial PDF function. Okay? And the Binomial PDF function requires three parameters. You have to put in n, comma, p, comma, x. Okay? So for this example, I want to type in Binomial PDF. N is 5, p is 0.75, and x is 3. Okay? The Binomial PDF function, if you go to go to second vars, and then click the up arrow, because Binomial PDF is at the bottom of the list. Now you'll see two things, Binomial PDF and Binomial CDF. For now, let's use the PDF. Later on, I'll tell you when to use the CDF. So Binomial PDF 5, comma 0.75, comma 3. Enter. And again, we get the same thing that we got before, 0.264, roughly. What does this mean? This means that, this means that there's a 26.4% chance of getting 3 green peas among 5 peas. Okay? Given that each of them is, there's a 75% chance of getting green peas. I've posted a calculator shortcut sheet on Blackboard. So if you look at that, that tells you which buttons to press to get to Binomial PDF. But again, you're going to go to second vars. Click the up arrow to get to the bottom of the list, and Binomial PDF is there. Okay. Let's do another example. Let's suppose I want to choose, let's look at an M&M example. Choose 8 M&Ms from a bag from a big bag. That's 70% brown. Remember we did this example before at the end of chapter 4 when I went over that practice sheet and I said we're going to look at this later. I want to know what's the probability of getting exactly 4 brown. This is the one where we wrote down binomial and we said we'll do it later. Okay. Well, can I use the binomial distribution here? Let's check our properties. The first thing is fixed number of trials. Do we have a fixed number of trials? Yeah. How many trials? How many M&Ms are we choosing? 8. Okay. Are each of the trials independent? Yes. How do we know that? It's a big bag. Remember, if it's a big bag, if your sample size, if your population is large, even if you choose without replacement, then you can consider it independent because the sample is so small compared to the population. It's like choosing a drop of water out of the ocean. It really won't make a difference. So it's even if I choose all 8 at once, which I'm going to do, it's not going to matter because the bag is so big. So yes, we do have independence. So I'll just write independence check. Is the probability of getting a brown M&M the same each time? So is the probability of success the same each time? Yes. And the probability of success is 0.7. Then what's the probability of failure? 1 minus 0.7 What's 1 minus 0.7? 0.3. So remember, Q is always 1 minus P. Okay? Here I want getting exactly 4 brown. So again, I can do binom PDF N P X. Again, that's N, P, and X. Okay? And you plug this into the calculator. Whoops, I went up too much. Binom PDF 8, comma, 0.7, comma, 4. And I get 0.136. So that's, is it 0.136 or? Yeah, 0.136. I can round it to 0.136, which is 13.6%. So there's a 13.6% chance that I'm going to get 4 M&Ms if I choose 8, if they're 70% brown. What's the probability that all 8 are brown? Well, I can use the binom PDF for this also. We did this last time. We did 0.7 to the 8, but you can also use the binom PDF here. 8, comma, 0.7, comma, I want all 8 brown, so X here is also 8. Now the cool thing, if you do second enter, it'll copy what you just put before, and all I need to do is go back and change the 4 to an 8, because I still have binom PDF there, and I get 0.057. So if you look back at that practice sheet that we did, this is what we got. So 5.8%. Or you can do 0.7 to the 8. 70% chance each time. We choose 8. Oh, whoops, I wanted to press 8. Yep. And what's the probability of getting none brown? Well, again, you can do binom PDF. 8, comma, 0.7. And how many brown do I want this time? 0. So you do second enter, that copies that. Second enter again, copies the previous thing. And I want to change this to a 0. So binom PDF. And this gives me a very, very, very small probability, roughly 0. And remember last time, what's the chance of if 70% are brown, how many are not brown? 30%. And I want all 8 of them to be not brown. So I think we did this last time, but I can check and show you that it's the same thing. Okay. So the binom PDF function is a very useful function to use. Now the question is, are any of these probabilities unusual? Is it unusual for me to get exactly 4 brown, all 8 brown, or none brown? Yes, this one is unusual. Why? Because it's less than 5%. The other ones are more than 5%, so they are not unusual. So think about it. If you have a big bag of M&Ms, 70% of those M&Ms are brown, it's highly unlikely. It's going to be very unusual if you pick a handful of 8 and none of those are brown, right? Then you're going to be like, okay, something is going on here. At least one of them has to be brown, because 70% of my bag is brown M&Ms. Okay, so we will continue this discussion in the next video, and we'll talk more about the binomial probability distribution.